All right, 2021, version B, exam 2. First thing we're going to do is some E and Z. So again, some rankings. Divide the alkene in half. Rank the things off of the carbons of the alkene. Fluorine, carbon. So even though there's bromine out here, this takes higher priority because we go one bond out at a time. So it's fluorine versus carbon. Fluorine has a higher atomic number. Carbon, carbon, tie. Carbon, carbon, hydrogen, hydrogen, carbon, 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 hydrogen. One carbon, the second carbon beats this one. So that's higher ranking, so they're on opposite sides. That's an E alkene. This one, oxygen versus nitrogen. Oxygen has a higher atomic number. Carbon, carbon, tie. Carbon to carbon, hydrogen, 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 hydrogen. Opposite sides, E. Draw the enantiomer and diastereomer for the molecule below. So enantiomer, everything's opposite. Diastereomers, at least one's different. So if you have the two hatches, the enantiomer would be everything wedged. So that's this. You have two possible diastereomers, right? You keep one the same. Flip the other one. Keep this the same. Flip this one. Both of them are diastereomers. You only needed one, so it didn't matter which one you picked. So the next ones, now we're determining whether they're constitutional isomers, enantiomers, diastereomers are identical. So you need to know what those terms mean. Right? Constitutional isomers, different bonding, same molecular formula, different bonding, different constitution. Enantiomers are mirror images. Diastereomers, hence di, you need to have at least two chiral centers, two asymmetric centers. So if you only have one, it can't be a diastereomer, right? So, or they're identical. So for this first one, they can't be. You automatically can eliminate diastereomers. It can't be a diastereomer because how many asymmetric centers does it have? Each one just has one, so it can't be a diastereomer. It's not a constitutional isomer because it looks like it's bonded all the same way. So then you're stuck with enantiomers are identical. And the way to figure this out, there's two ways. You could do R and S and do it. Or you could just look really quick and say, okay, everything's on the same side here. What's different? This methyl's wedged and H is hatched. And over here, the H is wedged and the methyl's hatched. So they flip that around. So that gives me the clue that there are enantiomers. So enantiomers here. Identical here. This is just after a ring flip or chair flip. Right? The OH is up, the methyl is down, axial up, axial down. Do the flip, pull this up, axial, equatorial down, axial up. So it's just a ring flip. So those are actually identical. So those are conformational isomers, like a Newman, like right. The molecule is just moving. Conformational isomers. So this was hopefully this was ended up being more of a tougher one than I thought it'd be, but they're exactly the same. You can just take this molecule, right? Just take this and you flip it over, and it ends up being the same thing as you have right there. So they're identical. This one, again, diastereomers are possible because you have more than one asymmetric center. You have more than one sp3 hybridized atom bond to four different things. So you have three stereocenters. Notice how these two are the same, they don't change. All of a sudden this one does. That's the clue to tell you it's a diastereomer. So at least one stereocenter being different. And then this one was also trickier than I thought it would be. These are just completely different molecules, right? They're constitutional isomers. They're the same number of carbons, hydrogens, and oxygens, but they have different bonding, different constitutions. So the wedges and hatches here have nothing to do with anything, just to confuse. Throw you off. This one is about did you understand how to basically stabilize carbocations? There's three ways: lone pair resonance, pi bond resonance, and hyperconjugation. So a lot of folks try to do rearrangements here. I'm not asking to do that at all. Just want to know the names of these things, and I only ask for a resonance structure for the first one. Right? So didn't want any rearrangements, didn't even want any resonance here even. Just recognizing that this can do lone pair resonance. Notice where the arrow goes between, right, to the bond. That makes this plus charged oxygen, but that's really stable because everybody has a full octet here, of course. And the other thing, so this is hyperconjugation. There's no resonance, but it has 9 sigma bonds, 3 bonds away, so that makes it stable. A tertiary carbocation. This is a primary benzylic. carbocation, and so this is really stable because of all the pi bond resonance it can do. So that's what I was looking for there. All right, so this one, a lot going on. Wanted to first, right, draw all the beta hydrogens in X. How many types are there? So there's 2 types. So from this spot, from the atom that has the leaving group attached to it, you go 1, 2 bonds away, 1, 2 bonds away, and there's these 2 and these 3, and they're different. So they lead to 2 different types of alkenes. So we say 2 types. Then it wants the reaction for each Y and Z. So how do I know what's going on here? You look at the nucleophile, because it's a secondary alkyl halide, so it's not giving away too much. The nucleophile is reactive. I know it's reactive because of the negative charge there. Right, so that tells me a lot. So that means it can't be SN1 or E1 because it's a reactive nucleophile base. So it has to be SN2 or E2. And so I look at the 2 products. This is a substitution. I know that because I'm substituting the bromine for something else. Also, I see inversion, right? Wedge to hatch. That tells me SN2. This is an elimination product. I already said it was reactive, so it can't be E1, so it must be an E2 product. So that's how I knew that. Here I said product Y is kinetic. That means it comes from the lower energy hill. And I said Z is thermodynamic, which means Z just is lower in energy than Y. Right? So kinetics is all about the heights of the activation energies. The Y and Z are all about the thermodynamics is all about the energy of the products. So there's the free energy diagram for that. And then this one threw people off too. Fill in the box with a reagent that'll give only Z. So if I wanted to only get E2, I want to keep the reactive base or nucleophile. I just need to make it bigger, bulkier. And so I just drew one example of what it could be. It could be lots of things. Biggest things you needed to have was a negative charge and a lot of carbons to make it bulky. That would work well. All right, last one on this page, little molecular orbital diagram. So just basically asking, did you realize, right, can you draw a molecular orbital picture for an SN2? So I wanted you to just draw some generic leaving group. It doesn't need to be iodine. You could literally just said leaving group if you wanted to. But I wanted you to show sigma star to show that it's 180 degrees apart, right? That's why you get inversion, is because the nucleophile needs to go to sigma star, where you put electrons in somebody's antibonding orbital that breaks the bonding orbital. So that's what I wanted to see here, to show that you knew where sigma star was at, you had some correct arrows, and showed some inversion, right? So that 180 degrees. The only other one we did a molecular orbital picture was with the E2. We did that anti-periplanar stuff. So these ones got hard for 2 reasons. The chair flip, you gotta make sure you can do that. And then folks got confused and forgot what it, like just reading, I'm telling you what the reaction is. I'm not hiding it, I'm telling you it has to be an E1. Right? So if you're essentially given the starting materials, given the reaction, you can draw, that means I'm telling you the mechanism, you should be able to draw the product. So you do the ring flip, so flipped it up, bromine axial, now it's equatorial and up, right? Actually, I drew, this should be down, that's silly, of me. That's a mistake. What? Shoot. Nobody said anything about it today. Ugh. Oh, golly. Gross. If you're down, you're down. My bad. So there's that. But E1, leaving group leaves, so you get a carbocation. You could have done a hydride shift. Some people got excited and did that. That's okay. And I was just looking for the nitrogen to take a beta hydrogen. Go there. And I did. You could have taken these hydrogens, but they're less likely because they lead to a disubstituted alkene versus a tri-substituted alkene, right? And according to Zaitsev rule, we want the more substituted alkene because that's more stable. So this one, again, ring flip, up, flip the stuff, pull this down like that. I wanted to get it axial because SN2 is going to be easier to see, so it needs to do, right? SN2 is 1 step, 2 arrows, comes to the back side, pops it up.
Thank you.
Right? And notice here is really important key here is this thing that added is now down, right? It's equatorial and down because the chlorine was axial and up. So the thing that adds is going to be the opposite side. And so in this case, it's going to be down. So it means it has to be equatorial, and they can show it this way as well. And make sure you balance your charge. The chlorine Cl- is there. All right, so for this one, draw the Newton projection shown. Got a staggered conformation, so right, if I drew my full person here, stand there. So the H is on my right, the ethyl, the Cl, and the H over here. My feet is methoxy, this H is there. And you need to rotate to get this H and this chlorine antiperiplanar. I rotated carbon 2, the back one. You could have rotated carbon 1, doesn't matter which one you want to do. You just need to get the H and this H and the other carbon, right? That's the other key. Make sure the leaving group is on carbon 1 here. The hydrogen then needs to be on the other carbon. It can't be on the same carbon, right? So you gotta get these two lined up, get them lined up. The neat thing to see here then, once you get them lined up, is you can see, right, the methyl and the H are on the same side. So the methyl and the H need to be on the same side. The ethyl and this O-methyl are on the same side. So make sure though, right, like this carbon had the O-methyl and the H. Make sure they're on the same carbon. Don't start flipping things around. Achieve makes you do a couple practice problems like that too. Some multiple choice questions, similar to what we practice on clicker questions. Not undergoing SN2, so this is just basically understanding, right? SN2 needs that backside attack. So tertiary electrophile, primary allylic, primary electrophile, primary benzoic, steric because of this one, so that's the one that won't work. This one, you have a plus charge and an O methoxy, right? You see that. Potassium, you realize that's an ionic bond. You see that the product here is a alkene. That should automatically help you eliminate any of the substitutions. And then you look at, is it reactive or not? That's a reactive nucleophile, so it can't be E1, so it has to be E2. So size doesn't really play a role here. So I'm telling you what the product is, so be careful if I tell you what the product is. Meso compounds, again, cut this in half, they're on opposite sides. Cut this in half, but they're different atoms. This one doesn't really work. You cut this one in half, you have a mirror plane right there. So that's the one you want. What reaction step does not happen in SN1? So SN1, substitution, so has a nucleophilic addition, has rearrangements, has carbocation formation, but eliminate, right? There are the words there. Beta hydride, I didn't said elimination. So that's not in an SN1 reaction, right? An elimination reaction. Here we go. We have a secondary allylic leaving group or electrophile, so it can be anything. So we look at the nucleophile. The nucleophile is reactive, but it's small, so that makes me think SN2. So if you do an SN2 reaction, and if I do an SN2 reaction, what's it going to be? Backside attack. Pick that up in the iodide. And make sure the key here is it was hatched and not needs to be wedged. So that's what you need along the way. Secondary look here, but you have a small nucleophile, but it's not reactive. It doesn't have a negative charge. So now I'm thinking SN1. First step in an SN1, or one of the first steps, you got to either make a good leaving group or have the leaving group leave. Iodine's a good leaving group. It leaves, make a carbocation. Folks wanted to do a couple things. You could do resonance here, but it leads to the same type of carbocation, right? This is secondary allylic. If you did resonance here, it'd also be secondary allylic. So there's no rearrangements to do, right? Can't make it any better than this. There's no resonance to do. Nucleophile adds. I minus comes and we deprotonate. And of course it's racemic, or you could just indicate that by showing no wedges and hatches. So I'm just looking for here was just basic mechanism arrows and resonance arrows, right? Just good arrow. I wanted this part to be kind of easy. So elimination reaction, right? If I bold or underline things, make sure you remember that is probably important. So starting here, going to these two things. So in this first step, leaving group leaves. How did I know that? All of a sudden there's the carbocation. Go down one more step. Looks like the plus charge hasn't moved, but a methyl has moved, but it looks like the plus charge moved, right? So do a alkyl shift, a carbon shift, get the plus charge there. So it's a tertiary benzylic, right? You can do some resonance. That's what I was asking you to do here. That's a resonance arrow. Then finally, what I want here, I want a elimination. right? The reason I knew that is because look what else I gave you, the other byproduct. All of a sudden there is no longer an O minus, there's an OH. So the H means you're taking an H. That should tell you it's an elimination, not a substitution. Plus, hey, I told you it's elimination, right? So you take the beta hydrogen. Why'd I take that one? Because this one leads to a tetrasubstituted alkene. There are also beta hydrogens here, but it leads to a disubstituted alkene. So you want to get the more substituted one because of the Zaitsev's rule.